All right. So last class we kind of started on, covering chapter one, and looks like we're about halfway through. But last time I mentioned, I kind of went over what will be on the quiz for next week, right? So we do have a quiz planned for next Friday, and that quiz will be over part of the periodic table, right? So elements 1 through 18 here. Remember, you should know 4 pieces of information for each element. That's the atomic number, the symbol, the name, and the atomic weight to 2 decimal places. So don't forget about that, right?
And that was just for the first 10, right, sir?
First 18.
18, gotcha.
Do you mind saying that one more time? We need to know the atomic symbol, the atomic number, 2 other things?
Yeah, the atomic number, the symbol, the name of the element, and the atomic weight there to 2 decimal places, right? And that's just for elements 1 through argon here, 18. Shouldn't be too bad. I kind of recommend just kind of like filling in a blank periodic table just from memory so you kind of master that. All right. Last time we also covered, the different classifications of matter. So this slide here is like a good summary of everything that we covered, right? So we kind of talked about all of these different forms of matters, right? So we left off here, which sort of give us a general depiction of sort of the major forms of, or the major states of matter, right? So matter can be in the form of a solid, right, liquid, or a gas. These are some of the major, there's more than 3 sort of states of matter also. You guys don't have to be aware of that, but here on Earth, most of the matter is going to be in form of a solid, liquid, or gas. Another type of matter that you may not, or a state of matter that you may not be familiar with is plasma, right? You've probably heard of plasma before. But our sun is composed of completely, plasma, right? And what all that is, it's plasma is just a bunch of components of atoms. So it's like electrons, protons, neutrons, but they're not together as an atom, right? They're just kind of free particles. If you kind of look at fire or flame, fire or flame, right? A flame can get hot enough to be plasma. Whenever molecules carry or particles carry enough energy, right, they will start to kind of ionize and be free floating within a certain space. But if we take a look at these different states of matter, solid, you can see these particles here are very, very close together, right? If you can imagine that. Liquid, right? Particles are not so close together. There's a little bit of movement, with each particle. It makes, the fluidity that liquid has. But when it comes to gases, the particles are kind of very, very far away from each other, right? And these molecules are able to move sort of in random directions, right? Think about a gas. You guys see my PowerPoint says pause for some reason.
Yeah, we can see it.
We can see it.
Okay. All right. If we look at like, we can imagine, what the different states of matter look like for water, for example, or H2O. We know that water as a solid forms what's known as ice, right? In the case of ice, you have these water molecules which are very, very close to one another. Their movement, each individual water molecule, its movement is more restricted, right? It's restricted by the sort of bonds that it forms between other molecules, right? Whereas in a liquid, these water molecules have a little bit more fluidity. There are like bonds between the water molecules, bonds that form between the water molecules, but these are kind of easily broken by the increased temperature within a liquid as opposed to ice, right? Then you think about gas, water vapor, for example, is water as a gas, right? Sort of a gas form. Right, so just kind of moving through chapter 1, we're going to talk about the types of changes. So a physical change, you guys should be aware of definition for a physical change. A physical change for a particular substance does not alter the composition or the identity of a substance. So what do we mean by that? All right, just to kind of give you an example, ice melting, right? Think about ice melting. Whenever ice melts, it goes from a solid form to a liquid form, right? In that process, in that change, that physical change, the water molecules themselves do not undergo any type of rearrangement. That makes sense, right? The water molecules stay as H2O. So I think, if you're taking the lab component of general chemistry, I think the very first wet lab you do is kind of studying physical changes versus chemical changes. But physical changes, there's no alteration in the water molecule itself. It's just the state of matter that's being changed here. With sugar dissolving in water, right? Sugar dissolving in water. Does anybody know the molecular formula for, let's say, glucose? Glucose is a sugar. Some of my biology folks may know. When molecular formula. So if you don't know, like the molecular formula is sort of the chemical makeup. Go ahead, right?
Isn't it C6H12, I think, and then O6?
Exactly, yeah, that's it. So you think about a glucose molecule. I know if you're studying glycolysis or something, back in high school when you were learning about cellular respiration or photosynthesis, right? You may have heard of glucose before. But glucose is sort of like a ring structure. It has a ring structure molecule that's composed of 6 carbons, 12 hydrogens, and 6 oxygens, right? All kind of connected in a particular arrangement. But whenever you take that sugar and you dissolve it in water, so you're going from like this powder or this solid substance to a more aqueous substance. So that's whenever a compound is sort of dissolved in water, it's considered aqueous, right? In this situation, the sugar molecule itself doesn't break apart, right? The identity of those sugar molecules do not change. Glucose kind of stays as a ring structure. Right? The only thing is they're dissolved, which means there's water molecules surrounding essentially each sugar molecule, each glucose molecule, molecule. So hopefully, you know, you have a grasp of that concept. Physical change does not alter composition or identity of substance. Chemical changes, however, and we'll be dealing with, you know, chemical reactions throughout this course, or looking at, you know, chemical reactions and trying to predict actually chemical changes that will occur, you know, for some chemical reactions. But a chemical change is a change that alters the composition or identity of a substance. One example of that is the production of water, right? From hydrogen and oxygen, right? So if you take some hydrogen molecules, and that's kind of shown here in white, hydrogen is a diatomic molecule that's composed of two hydrogens connected to each other, right? Two hydrogen atoms connected to each other. Oxygen is also a diatomic molecule. By the way, I'm saying these diatomic molecules, does anybody know any other natural diatomic molecules?
Isn't one chlorine?
You said chlorine?
Yes.
Yeah, chlorine is definitely one. I think somebody's about to say something. Chlorine exists as Cl2, so two chlorine atoms. Yeah, and that's a gas.
So isn't it O2 as well?
Oxygen, right?
Yeah.
I think there's like 7 naturally occurring
Iodine.
iodine. Yeah. All right. Yeah, there's hydrogen, there's fluorine, right? Anyway, we'll talk about all of that a little later on, but whenever, you know, we can combine hydrogen, oxygen in such a way, as long as we supply some energy to it, in this case,
Join the meeting.
burning it, so we're applying some fire to it. The molecules are sort of rearranged in such a way that we form an entirely new substance, right? Which is water, H2O. So this kind of represents a chemical change here. Whenever you have a rearrangement of these atoms to form new substances, new compounds, right? It's a chemical change. So make sure you guys can kind of decipher the difference between a chemical change and a physical change. Not only just by, you know, the definition, but by example, right? Okay. Another thing are properties, right? So a lot of times whenever we're trying to characterize material or, you know, identify certain material, there's a lot of things we have to kind of observe about this particular material. A lot of properties you have to note about these particular material, right? And these properties can be sort of categorized or grouped into 2 major forms of properties, right? You have extensive and intensive. Right? So extensive properties of a material depends on how much matter is being considered, right? So, for example, the mass of a particular material, the mass of a substance, right? The length of a substance, and as well as the volume of a substance. All of these are properties of whatever substance you're studying, right? But each of these properties here depend on how much material is being considered, right? So the mass of something, right? the mass of something depends on how much material is there. Right? So if you have a smaller amount of, let's say a smaller size apple, right, versus a bigger apple, which has, you know, a greater amount of material. Right? It's a bigger apple, right? The mass here will sort of change between those two, the smaller apple and the bigger apple, right? So the mass there is going to depend on size, right? Same thing with length, right? How long something is depends on how much of that thing is there, right? And so those are extensive properties. Intensive properties, on the other hand, of a material does not depend on how much matter is being considered. So, for example, density. Does anybody know what density refers to? But I have a general idea of what density is.
How many, like, I guess you could say molecules are condensed together to make it like heavier?
That's a pretty good definition there. Exactly. So it's the amount of atoms or the amount of material condensed in a particular volume. That's right. So actually, to calculate density of any object, as long as you know the mass, you know how much it weighs, as well as the volume, you can calculate density as a numerical value for that substance, right? So maybe you guys kind of recognize the mathematical formula for calculating density, mass over volume, right? We'll talk about that, you know, also. But yeah, density is an intensive property. It doesn't matter, although, you know, density depends on the weight and volume, mass and volume, the ratio between mass and volume, mass divided by volume, right, is sort of a constant value. Let's see if let's say I take a pizza, right? A round pizza. It has a certain weight to it, right? Certain volume to it. It has a particular density, right? Circular pizza. But if I cut this pizza in half, right? If I cut this pizza in half and try to calculate the density of half of that pizza, the weight of that pizza is now half, the volume is now half, right? So the ratio between the mass and volume doesn't really change, if that kind of makes sense. So the density is kind of the same, whether you have a small amount of pizza or large pizza. Anyway, temperature, the temperature of something, right, doesn't depend on how much material is there. And also color, right? You're looking at a smaller apple versus, and they have the same color, they're both red apples, right? The property of the apple, the color property, right, is red, no matter the size, right? So make sure you have a good grasp of, you know, the difference between those two. Here's our definition of matter again. Anything that occupies space and has mass. Right? So let's talk about this mass here. What is mass? Right? So mass here is a measure of the quantity of matter, right? And usually mass is universally measured in kilograms, right? I know if you're weighing yourself, really in any part of the world except for United States, you know, they use kilograms to kind of weigh or measure a person's weight, body weight. In America, we use pounds, right? Does anybody know their weight in kilograms? Oh, okay. I think I should weigh around like 80 kilograms. Anyway, it's a measure of quantity of matter, that matter being myself, right? Not to get that confused with weight though. Weight is actually defined as the force of gravity that exerts on an object, right? Now, here on Earth, actually mass is pretty equivalent to weight, although they differ in terms of their definition. $72 kilograms. Let's say you go to the moon, right? Go to the moon where there's less gravity. Of course, probably seen these pictures of astronauts kind of, leaping across, how do I say, leaping or, kind of floating a little bit on the moon, right? So their weight on the moon is obviously less, right? In fact, it's like a tenth of, I guess you weigh 10 times less on the moon, right, than you do on Earth. But however, his mass hasn't changed, right? The amount of matter for this particular astronaut, for example, hasn't changed, right? But in terms of weight, his weight has changed, if that makes sense. Just as an example here, 1 kilogram, 1 kilogram bar will weigh 1 kilogram on Earth, but it'll weigh 0.1 kilogram on the moon. All right, now we're gonna get into the fun stuff. Not really. Let's get into all of these different units of measurement, right? And what we're looking at here is a table. This table is also found in your book. It's called the International System of Units. These are sort of universal unit of measurements, right? Particularly in the sciences. In the sciences, we sort of relay information across the world. We don't keep information just within the United States. So measurements kind of have to be universal. So length here is often measured in terms of meters, right? If you think about other ways length is measured, especially here in America, we like to use feet a lot, right? Or miles. But meter is kind of like a universal standard. Measuring the mass of something, we often measure that in what's called kilograms, right? The symbol for that is kg. Time is usually measured in seconds. Electrical current. Temperature is in Kelvin. You may not have heard of Kelvin before. Probably you're used to Fahrenheit, right? Where, the rest of the world, they use Celsius, especially when they're reporting, the weather. They'll give the weather in terms of degrees Celsius, right? All right. You guys should also know some of the common prefixes used with these units. Right. Maybe you heard of like centimeters before, centimeter. Centi is actually a prefix. And it's also on this table, centi. And really it's the scale of which, you know, the scale of which the length is measured in terms of meters. Right? So 1 centimeter is equal to 0.01 meters. Right? A lot of times if you're measuring really, really small, you know, really small things, it's better to kind of use centimeters rather than using meters, because you have all these decimal places when you measure, like when you're measuring something small. It's kind of better to put it in centimeters. Whenever you're measuring like long distances, you want to measure the distance between Earth and Mars, right? You wouldn't use meters or you wouldn't use centimeters, right? You probably put that on a scale of tera or giga, right? Gigameters. Much easier to work with these numbers. So you guys have to know this. What you have to know here is these prefixes. Prefixes, the symbols for these prefixes, and their equivalents to sort of the standard unit, right? In our calculations and, whenever we come to the exam time and in your homework, right, you're going to be performing calculations that convert between these prefixes, right, or convert between decimeters and meters, right? So here, as an example, 1 decimeter equals 0.1 meters, but how many meters is equivalent to 553 decimeters? So there's calculations that you can carry out to do that. But for now, initially, you need to know these prefixes and you need to know their equivalency to sort of the base unit. All right. So I think you guys can do that. Can you guys do that? Sort of memorize these prefixes and right, their meaning, right, or definition.
Yep.
All right, appreciate that. Okay. Volume, or we talked about volume as one of our extensive properties. Right? But if you've never heard of volume before, what is volume? The definition here.
Something takes up in 3 dimensions.
Amount of space, yeah. So yeah, here's our definition here. Actually, yeah, you said the definition. The amount of space something takes up in 3 dimensions, right? So the one of the common units as far as measuring the volume of something is in cubic meters, right? So meters cubed. And as David said, the amount of something, the amount of space something takes up in 3 dimensions would give you sort of a cube area of measurement, right? So if you think about finding the volume of a block, right? To find the volume of this block, you need to know three things, right? You need to know the length, the height, and the width, right? Multiply all those things together, you get the volume. So that kind of goes back to what, geometry, algebra, geometry. Finding those formulas, volume of a square or of a block, I'm sorry. So yeah, often, we use meter cubed or centimeter cubed, depending on how big the thing that we're measuring is for solid material. Let me just kind of skip through this. But oftentimes you'll see volume, especially in this class, measured in terms of milliliters or liters, right? So, and this is common, we use milliliters or liters whenever we're measuring liquids. Right? So if you think about a 2-liter Coke, right? You don't say 2 meter, a 2-meter cubed Coke, right? A 2-liter Coke or 1-liter Coke of Coke, right? Yeah, so there's this equivalency between these sort of units for volume. 1 milliliter is equal to 1 centimeter cubed, right? Yeah. Density, one of those intensive properties, right? So the unit of measurement for that is kilograms per meter cubed. To calculate density of an object, right, you need two pieces of information. That's its mass as well as its volume. This ratio between mass and volume will give you a value for how dense something is, right? A lot of times, in a research setting, especially in my my area, right, it's important to kind of know the density of different solvents and different liquids that we use, right, in order to extract out particular compounds. Right? Because compounds like to, compounds in a mixture will separate based on how dense they are, right? And if you can separate out compounds based on their density, you can isolate, particular compounds which may be of interest for drug therapy reasons, or antimicrobial reasons, or things of that nature. But it's definitely, you guys definitely should memorize this definition. Density equals mass over volume. If you look at the units here, sort of the standard unit for density, kilograms over meter cube, you'll see that kilograms here is a unit for mass, right? Whereas meter cube is a unit for volume. Right? So the unit here is a ratio of mass over volume. Let's take a look at an example real quick. Thinking about this question, actually, let's see. If you guys are still tuned in, right? I want to see what you guys come up with as far as your answer. If you could just kind of put that in the chat, and if we can get like a survey of different, hopefully the same answer. That'll kind of help me see who you guys are. So in this situation, we have a piece of platinum metal, which has a particular density, right? And this metal has a volume of, what is it? 4.4, no. Saw my answer. 4.49. What is its mass, right? So you'll often, run into problems like this where you have this situation. They want you to calculate the mass from the density and volume of a metal. Right? How would you solve this? What was your?
I got about multiplying.
Multiplying?
Yeah. I multiplied the density and the volume.
Okay, like a good strategy there, good direction. I see a lot of the same answers there. I think most people are spot on. So this is, a situation where here, you just try to figure out what you're looking for, what you're trying to solve for. Here we're trying to solve for mass. We're given density, we're given volume. How do we rearrange this equation? Seen in the chat, somebody put a rearrangement of this equation. And you also mentioned if we rearrange this equation, we can multiply density and volume together. That'll give us mass, right? One thing I would be careful about, or kind of warn you guys about, is making sure units cancel out, right? Whenever you're multiplying density by volume, you have to multiply it such that the units for density and the unit for volume kind of cancel out, such that you're left with a unit for mass, right? Which in this case should be grams. And only have. So your answer, okay, good question. It's like Jana said, don't we have to convert? So let me pull up the answer there. Solving this problem, we should get 96.5 grams, right? This is what a lot of y'all said. Somebody mentioned, should we convert this mass to kilograms, right? Since kilograms is sort of the standard unit for mass. I would say no, right? Because this problem specifically doesn't ask us to convert to kilograms. But yeah, you will run into problems where they say, oh, convert your answer to kilograms or nanograms, right? And you have to be able to know how to do that. So in this particular case, I wouldn't go that far. We might need our answer in grams. Right. So since density is an intensive property, it's not going to change for a particular substance, right? Air is always going to have the same density. And that is 0.001 grams per centimeter cubed. This is a very, very low number, right? Which is why air molecules float on top of everything else, right? And there's a list of some common substances and their specific densities, right? Looking at this, I like to use this example. Right? Let's say I had a diamond watch, right? All diamond watch on one arm and an all gold watch on the other on my other arm, right? And they were the same size. Which watch would be heavier, right?
The gold,
Diamond watch, gold watch.
yes,
And why do you say that?
because it has a greater density.
Well, that's greater density, right? If they were the same size or having the same volume, then because gold has this greater density, the mass of that gold watch would definitely be a lot greater. Oh, good, yeah. And of course, if you know, comparing, let's see, oil on here. What about oil and water? You think about oil and water, they don't mix. Which substance float on top of the other? Which one has a greater density? Right?
Water.
What's the?
Water has, say again? I think I heard water may have a greater density,
Water has a greater density.
right? So that means oil floats on top of water.
Oh, yeah, that's what I was saying, but I don't know.
I think you do know, yeah. So yeah, that's right, right? Oil does sit on top of water, right? They don't really mix. All right, good. So got that. Okay. I think next class, which is Monday, we'll get into the different temperature scales, right? Kelvin, Celsius, Fahrenheit. We'll talk about these and also some calculations associated with converting between these different temperature scales, right? Okay. So we'll stop here and pick up Monday. So thank you guys for coming, and I'll see you next week.
Have a good
Yes,
week.
sir.
Bye.
Thank you. Have a good day.
You have a great day.
Have a good day.
Thank you. Have a good day.
All right.
Thank you.
Oh, yes, yes. Mhm. Oh, tonight, I think I emailed you back about, you said you were in section 3? Okay, you're in section 4. Oh, this is, we have, multiple general chemistries, and some of the chemistries are taught by other professors. The
Me, same. I'm just now joining the class as well.
Okay, and yeah, you guys didn't miss too much. All we did was